right, so we have a box with a square base and an open top. So this is your open top here. Square base means it's got x and x as variables for the two bases on the bottom, and we'll call the height of it, we'll just call that y. So the volume winds up being base times width times height, which is x squared times y. And the area, since there's only one bottom and no top, it's got a single x squared, and then 4 sides, which are each x times y, and then that equals a total of 1,300 square centimeters. Okay, so we'll take this, this is our constraint, and we'll solve it for one of the variables. The easy one in this case seems like it's y, since it's linear in each equation. So we'll just take, maybe subtract x squared from both sides here, so that 4xy is equal to 1,300 minus x squared. Drop the units, don't need them right now. Divide both sides by 4x, and you'll end up with an expression 4y in terms of x, which ends up being 325 over x minus x over 4. And what you then want to do is you want to take this expression for y, plug it back into the volume equation so that we can have a volume as a function of x. So the volume as a function of x winds up being x squared times that y expression, which was 325 over y, sorry, 325 over x minus x over 4, I believe is all it was, right? Yeah, once you reduce. And then if you distribute this x squared through, you'll get that the volume as a function of x is really 325x minus x cubed over 4. This is now a single variable equation, so we can take a derivative and optimize it. So we'll do v primed of x, first derivative, 325 minus 3x squared over 4. And if you set this equal to 0, looking for that critical point, you'll get basically that 325 equals 3x squared over 4. Multiply both sides by 4/3 and take the square roots, and you'll get that x ends up being, well, it's a positive square root of 1,300 over 3. Now, if you technically could get a negative root there, but since x is a side of a geometric object, we're only going to consider the positive value. The negative value just is erroneous in this case. And then what we want to do is we want to, this is your optimal side length for the base. Now they wanted the maximum volume, so we can just take that and plug it back up into the volume equation that I had solved for x. And if you do that, let's see here, the volume of the square root of 1,300 over 3 winds up being 325 times root 1,300 over 3, and then minus something like 1,300 over 3 to the 3/2 power divided by 4, which, you know, punch that into a calculator to get a decimal approximation. You wind up with something like 4510.276 cubic centimeters. Okay. And that is your maximum volume. How do we know it's a maximum? Well, we could do a couple different things. I mean, if you just look at, we could take a second derivative, actually, and get that it's negative, right? Just from here, the double primed would be, let's see here, it would just be negative 6x over 4. And if you plug in a positive number, this is going to be less than 0, which means concave down whenever x is equal, whenever x is positive specifically, which means that this is a maximum value. And that's it. All right. There you go, maximum volume.